So good afternoon once again. Today we are going to study the next parameter in the plastic part design, and that is allowances in the plastic part. So we have covered the concept of tolerances in the previous lecture. There are a number of aspects which I already told. List was given by me in the previous class. Tolerances, allowances, then design of rib wall thickness, that is minimum wall thickness, design of hole, then undercut, inserts, etc., etc. So today in that sequence, next next important parameter is allowance. Now allowance means extra dimension provided. You know that in the subject manufacturing process we have studied this concept, as extra dimensions are provided on the pattern for overcoming the number of things such as shrinkage, solidification, then machining, distortion, etc., etc. Now, as far as plastic part is concerned, to achieve the correct part dimension, the number of allowances provided includes shrinkage allowance and draft allowance. Aim is to achieve correct dimension. Aim of any process is to achieve correct dimension. So in this case, to achieve correct dimension, the major important allowances considered here are shrinkage allowance, and second one is draft allowance. Now these two are important aspects of the allowances. As far as this shrinkage allowance is concerned, you know that plastic material have different properties as per different chemical structure. So polypropylene is different, polyethylene is different, PVC is different, polycarbonate is different, as per nylon is different. As per different combinations or as per different structure, the allowances such as shrinkage allowance varies, because every material shrinks in different way. Every material shrinks in different way. So here your nylon, polypropylene, PVC, polystyrene, number of materials you are using for making the components. Now if you use nylon material for XYZ component, what will be the shrinkage allowance considered? If you use polypropylene, what will be the allowance considered? So you can write one statement: the allowance, shrinkage allowance varies with type of material, because every material have different shrinkage properties. I repeat, every plastic material have different shrinkage property. So as per the material, allowance provided are, you can draw this table as nylon 6, so allowance provided is 1 to 3. It is percentage allowance, 1% to 3% allowance if nylon 6 material is used. So that you have to consider in the dimensions. I will make it more precise. It is 1 to 1.5%. Then if you use polypropylene, short form is PP, then it will be 1.2 to 2%. It is percentage allowance in the dimension. Then PVC soft, for PVC soft, the allowance provided is 1 to 3 mm. Then PVC hard, (0.5 to 0.7). Then polystyrene, it is same 0.5 to 0.7, and acrylic 0.3 to 0.6. So these are the number of allowances in different percentage as per the type of material which you are using for molding purpose. Now, even this allowance is to be considered while molding the plastic part. This shrinkage varies with different parameters. Means, if you select one particular material, suppose polypropylene, then for same material, if process parameters will be changed, the shrinkage will be different. I repeat once again, when we say that every material have fixed shrinkage properties, but if during the working, if process parameters will change, then your shrinkage behavior will be different. I am going to show the different curves, plots. So which are these different process parameters which are considered? So first process parameter is holding pressure, then melt temperature, mold temperature, holding time, and then wall thickness. When any of the parameter will be changed, you will find different shrinkage behavior. So this question was asked earlier for 3 marks. What is the concept of allowances and on which factor it depends? So let us see different plots for different parameters. I hope you have taken it down. Shrinkage, write down, shrinkage depends upon number of parameters. Shrinkage depends upon number of parameters. So first parameter is holding pressure. So you can draw plots along with me. Here I will write shrinkage. I will make double underline to the name of parameter. First parameter is holding pressure. What this graph is showing, as holding pressure increases, shrinkage decreases. Holding pressure means what? You are going to hold the mold walls. This is one half, this is another half. These two halves are held together with the help of mechanical clamp or hydraulic or pneumatic clamp. If you hold this tightly, then it is observed that shrinkage decreases. So holding pressure plays important role in controlling the shrinkage. Even shrinkage is behavioral property of the material. Every material has some different shrinkage. In that property, variation in the shrinkage for same material. I repeat once again. Variation in the shrinkage for same material is possible by changing this holding pressure. Okay. Now, second one is mold temperature. Shrinkage and mold temperature. See the graph now. Exactly reverse. It is exactly reverse of this. As mold temperature increases, shrinkage also increases. Mold temperature means what? This is mold wall. This is one half, this is another half. So these two houses are, if they are hot, very hot, material inside is hot and wall may also be hot. So mold temperature, if it is more, chances of shrinkage are more. So please see these two graphs. First graph is holding pressure. If holding pressure is more, as holding pressure increases, shrinkage decreases. But as mold temperature increases, shrinkage increases. Now second is wall thickness. Third, as wall thickness increases, shrinkage increases. Graph is similar to mold temperature. This graph, whether it is visible, just check. Wall thickness. Wall thickness. This third graph is wall thickness. As wall thickness increases, shrinkage is more or shrinkage increases. That's why it is recommended that your parts should have minimum or optimum wall thickness. So first parameter is holding pressure. Second parameter is mold temperature. Third parameter is wall thickness. Fourth parameter is holding time. Now holding time, see the beauty. It is similar to first plot, but up to certain level and again start increasing. As holding time increases, shrinkage initially decreases, but after it will start increasing. So optimum holding time is required, optimum holding time. Up to this, you can have decrease in the shrinkage, but after that, it may start increase in the shrinkage. So holding pressure, how to remember this? You may get confused, where to increase, where to decrease. So simple logic, we remember, mold temperature increases, shrinkage increases. Wall thickness increases, shrinkage increases. Holding pressure increases, shrinkage decreases. Holding time increases, shrinkage decreases. And next one is melt temperature. Melt means your plastic. Plastic melt temperature. Now it is having some optimum effect. See this. It is not giving much a deep slope as like other graphs. So shrinkage almost, if it is more initially for melt temperature, if melt temperature increases, it will give little decrease and again increase. So I repeat, these are the 5 parameters for shrinkage. First one is holding pressure. As holding pressure increases, shrinkage decreases. Second is mold temperature. As mold temperature increases, shrinkage increases. Wall thickness. As wall thickness increases, shrinkage increases. Next one is holding time. As holding time increases, initially shrinkage decreases, but later on it go on increasing. And next one is plastic melt temperature. It will have not that much deep effect. So initially increases, decreases and again increases. So draw all these 5 plots. So you have to write in the text also. Whatever I have explained, you can write this in the text. One by one, you write down these parameters. Parameters are holding pressure, mold temperature, wall thickness, holding time, and plastic melt temperature. Just 1 minute. So I hope you have taken these all plots: holding pressure, mold temperature, wall thickness, holding time, and plastic melt temperature. Now, second parameter of allowance, or second important allowance, is draft allowance, and that you know that some degree of taper is required for easy removal of the component. It is similar to the part or process which you have studied in casting. So A was shrinkage and B is draft. Now, draft allowance is for easy removal of the plastic part from the mold. Mold is metallic now. Mold is metallic. Mold is not sand mold. So that you can see. Excuse me, sorry. So concept is different here. In case of casting, allowance was provided on the pattern so that you can remove that pattern easily by leaving behind the mold cavity for easy removal of the pattern. Now here your plastic component, so allowance itself is provided in the mold wall, so that whatever plastic you are going to inject during injection mold or any of the process, that part is little taper provided, so that if you try to remove it out, it can be easily removed out. Okay, so that's why this considering the easy removal of the plastic part from the mold, taper is provided on the outer side walls. Taper is provided on the outer side of wall, and this draft angle varies from 0.5 degree. So usually it is, most of the cases range from 1.5 degree to 2 degree as per the side of consider normal to the plastic injection mold. Means which is your withdrawn direction. So your part, when you are putting in the part, even you see this duster, if you see this from outside, you may feel that yes, it is rectangle, but if you see it carefully, little draft is provided here. So your shape is not exactly rectangle, little taper is provided here. So why? Because it has removed from the wall. It may be in this way. If this is the mold wall, maybe in this way. When this is open, this part is taken out and it will fall down in the bin. So draft is nothing but the angle. You can write down 2-3 lines for the draft. For easy removal of the plastic part, from the mold after solidification, comma, draft in the direction of mold movement is provided. Draft in the direction of mold movement is provided. Full stop. It is the degree of taper provided for easy removal. It is the degree of taper provided for easy removal. Degree of provided for easy removal. Draft angle of 1.5 to 2 degree per side. Draft angle of 1.5 to 2 degree per side. For normally injection molds. Normally for injection molds. So usually the draft provided is 1 degree, 1.5 degree to 2 degree, 1.5 degree to 2 degree. So this is about the shrinkage and draft. So the title is allowance. The parameter of part design is after tolerance is allowance. Allowance is provided by 2 ways. First one is shrinkage allowance, second is draft allowance. What are the different sub parameters for the shrinkage? That is holding time, holding temperature, mold temperature, holding pressure, melt temperature, plastic melt, plasticized temperature. All these sub parameters, how affects on the shrinkage, that also we have covered in the allowances, and this is draft to be considered for easy removal of the solidified plastic outside the mold. So this is all about the allowances. Next important parameter which we are going to consider in the part design, that is rib design. Many of you may not know what is this rib. I will show you what is rib. Now, if I will tell you what exactly rib means. Rib is extra support provided to the plastic component for increasing its stability, increasing its strength. If you see the chair, now currently I have new design chair, but little old design plastic chair, if it is with you, which we are using at our residence. If you see at the back side, the extra attachment is provided there, that is support, called as a rib. So for example, if this is the leg and this is the base of chair, then here you are observing some ribs are provided. This is called as a rib. Or if you have some different wall, for example, if this is your bush, yes. Now let me show you this chair. See, in this chair, all these are ribs. What is this? These are called as ribs. Wherever you are observing, this is for extra support provided for increasing the strength of this. This is called as rib. Now, wall thickness and rib thickness, this different consider there, and one more rib is provided here. Okay, so if you see this here also, see, these are called as ribs. Ribs are provided for giving strength to the plastic component. Now, there are different parameters. If you don't consider the rib, if you don't design the rib, or if you don't apply the rib design in your plastic part, there may be chances that whatever wall thickness you have designed, there may be failure of your part with extra load wherever it is applied. For example, let us see, if this is one bush, I will draw 3D dimension. This is one bush. Try to imagine this wherever I put my finger here, this is a hollow part and this is the extended part in between. This is outer thickness, this is inside part, and here this in between, this is a hollow part. Now, if you want to increase the strength of this bush, if you use this in this way, what will happen? And now I will modify this design. What will happen? Just check. This is your old, and now what I am doing, check. These are vertical walls which I have provided, which gives extra support to this inner cylinder. This complete part is of plastic. This inner cylinder is not have that much strength in case number 1, but in case number 2, this complete part is having more stability. Are you getting? So that you have better strength for this component than this component, and these are called as ribs. These are called as ribs. So rib design, what are the parameters? I hope you understand what is meaning of rib. So just write down the statement. Many times, 1 minute. Just 1 minute. Sorry, there was a little disturbance. Write down. Many times, stiffness of the part. Many times, stiffness of the part must be increases to sustain the load applied. To sustain the load applied. And one of the easiest way is providing the rib. One of the easiest way is by providing the rib. Rib increases structural strength. This statement is very important. Rib increases structural strength. What are the aspects? See, there are following aspects for rib design. In bracket, guidelines. There are following aspects in rib design. In bracket, guidelines. So there are three important guidelines. Let's see one by one. First, a term statement. Rib thickness should be, now remember, whatever guidelines I am explaining you, many times these guidelines are asked in the terms of MCQs in the examination. So remember it well and write down without fail. Rib thickness should be less than wall thickness. Rib thickness should be less than wall thickness, and it is recommended around 60 to 80% of wall thickness. Rib thickness should be less than wall thickness, and it is recommended around 60 to 80% of wall thickness. So this is TR, thickness of rib, and this is wall thickness, your main thickness. This is a rib. So thickness of rib is around 60 to 80% of wall thickness. Means if wall thickness is 1 mm, rib thickness should be 0.6 mm to 0.8 mm. I repeat once again. If wall thickness is 1 mm, rib thickness should be 0.6 to 0.8 mm. This is the first guideline for rib design. Second guideline, write down. The height of rib be 3T. H is equal to 3T. T means wall thickness. The height of rib be 3T, and space between two ribs equal to 2T. Height of rib is equal to 3T, and space between two ribs is 2T. Same figure I will draw. See this. This H is equal to 3T. This is equal to T. And this distance is 2T. This distance is equal to 2T. Draw this. Height of rib must be 3T, and space between two ribs is equal to 2T. T is nominal wall thickness. In case of thick rib, third, in case of thick rib, there will be core out from the back. There will be core out from the back to maintain uniform wall thickness. Now see, this is your uniform wall thickness. This is a rib, and it is core out from the back. So part instead of making this thick, if you find this rib thickness is more and wall thickness is less, it is made hollow in this way. It is made hollow in this way. Rib to maintain minimum wall thickness. Rib to maintain minimum wall thickness. And one important statement write down. Ribs are placed along direction of maximum stress and deflection. Ribs are placed along direction of maximum stress and deflection. Just a minute now. Okay, friends. So today we have covered two important parameters of the part design. First parameter was allowance. Second parameter was rib. So in yesterday's class, earlier class, we have completed tolerances. Today we have completed allowances and rib design. So these parameters, allowances, we have covered shrinkage allowance, draft allowance, how different sub parts varies with the how the shrinkage varies with different sub parts like holding time, holding pressure, wall thickness, etc. Then rib, what are the guidelines for rib design? Rib is the extra part or support provided to the walls for increasing the stability of the part, for increasing the strength. Ribs are placed along the direction of maximum stress side and deflection. So there are three different aspects considered for rib design. First thing is rib thickness should be 60 to 80% of wall thickness. Rib thickness should be 60 to 80% of the wall thickness. Height of the rib should be 3T. The distance between two ribs should be 2T. Then if your rib is thick, then you have to modify the design of rib so that there will be core out and your rib will become hollow part in this way. These are the considerations for rib design. In next class, we are going to see what is wall thickness and what is undercut and what is hole design. So today we will stop here. Thank you. Okay, you can leave now.